What if everything you thought you knew about space and time was just the tip of the iceberg? Picture this. The fabric of the universe isn't just empty nothingness. It's a dynamic, bending, twisting stage where the laws of physics play out in ways so bizarre, they'd make even the wildest sci-fi movies seem tame. Think of Interstellar, where astronauts slip through wormholes and time stretches like taffy. But here's the thing, those mind-bending scenes aren't just Hollywood magic. They're rooted in real science, in the mind-blowing concept of space-time, the very framework of our universe, and today we're diving deep into its secrets. Space-time isn't just some abstract idea scribbled on a physicist's chalkboard. It's the invisible grid that shapes everything we experience. From the way planets orbit stars to the reason you can't travel back in time to fix that embarrassing haircut, space-time is the silent conductor of reality itself. And yet, most of us barely give it a second thought. But what if I told you that black holes can warp time so severely that a single minute near one could equal years elsewhere? Or that the universe might be threaded with invisible cosmic shortcuts called wormholes? These aren't just fun thought experiments, they're real possibilities that scientists are exploring right now. That's why we've packed this video with 30 astonishing facts about space-time, each one more jaw-dropping than the last. We'll unravel how time slows down when you're moving at lightning speeds, why the universe might be a giant hologram, and whether parallel dimensions could be lurking just beyond our perception. This isn't just a list, it's a journey through the most thrilling frontiers of physics, where the rules we take for granted start to bend and break, so buckle up. By the end of this, you'll never look at the night sky or the clock on your wall the same way again. The universe is far stranger, far more mysterious than we've ever imagined. And it's time to explore it together. Einstein's theory of general relativity flipped our understanding of the universe on its head. It showed us that space and time aren't just separate, rigid backdrops, they're woven together into a single, stretchable fabric called space-time. Picture a trampoline stretched tight. When you place a bowling ball in the center, the fabric dips and warps under its weight. Now, if you roll a marble across that trampoline, it won't travel in a straight line, it'll spiral inward, pulled by the curve the bowling ball created. That's exactly how gravity works in our universe. Planets, stars, even entire galaxies act like cosmic bowling balls, bending the fabric of space-time around them. The deeper the dent, the stronger the gravitational pull. But here's where it gets even wilder. Space-time isn't just bending, it's dynamic, rippling like the surface of a pond. When massive objects like black holes collide, they send shockwaves through this fabric, creating what scientists call gravitational waves. These waves travel at the speed of light, stretching and squeezing space itself as they pass by. In 2015, researchers detected them for the first time, proving Einstein's century-old prediction right. Think about that, the universe isn't silent. It's constantly humming with these invisible vibrations, a symphony written in the folds of space-time. And it's not just about gravity, time itself gets warped by this cosmic fabric. The heavier the object, the more it slows time down like a cosmic remote control hitting pause. Near Earth, the effect is tiny, but near a black hole, a single hour there could mean decades back home. That's not sci-fi, it's hard physics. So next time you glance at the sky, remember, you're not just looking at empty space. You're seeing a vast, invisible tapestry, bending and twisting under the weight of everything in it. And we're all just riding the ripples. Ever wonder why time feels so absolute when in reality, it's more like a river that flows at different speeds? Take a clock and place it at the bottom of a skyscraper. Now take an identical clock and put it at the top. Leave them there for a while. When you check back, you'll find something bizarre. The clock at the top has ticked ever so slightly faster than the one below. This isn't a trick or a manufacturing error. It's gravitational time dilation in action. a mind-bending prediction of Einstein's relativity where time itself stretches and slows depending on how close you are to a massive object. The closer you are to something with enormous gravity, like a black hole or even a planet like Earth, the more time drags its feet. Near a black hole's event horizon, the effect is so extreme that a few minutes for you could mean centuries for someone far away. Think of it like walking through waist-deep water. Every step takes more effort, and you move slower compared to someone on dry land. Gravity does the same thing to time. But here's the truly wild part. This isn't just theoretical. It affects us every day. Take the GPS satellites orbiting Earth, for example. They're about 12,000 miles up, where gravity is weaker than on the surface. Because of that, their onboard clocks actually run a tiny bit faster, about 45 millionths of a second per day. Doesn't sound like much, but if engineers didn't account for this, your GPS would be off by nearly 7 miles within just a few hours. That's the real-world power of time dilation, and it gets even stranger. Imagine two identical twins. One stays on Earth while the other travels near a black hole. When the spacefaring twin returns, they might be years or even decades younger than their Earth-bound sibling. Time didn't just feel slower, it was slower. So next time you glance at your watch, remember, it's not just counting seconds, it's measuring your place in the ever-flexible fabric of space-time. One of the most startling consequences of Einstein's relativity is something called the twin paradox, a thought experiment that sounds straight out of a time travel novel but has real-world proof. Imagine two identical twins. One stays on Earth living a normal life, while the other boards a spacecraft and rockets away at close to the speed of light. After a few years of high-speed travel, the spacefaring twin returns home, expecting to reunite with their sibling. But here's the kicker: the Earth-bound twin has aged decades, while the traveler has barely aged at all. This isn't just theoretical. Time dilation, the slowing of time at high speeds, has been tested with incredible precision. In the 1970s, scientists placed ultra-accurate atomic clocks on commercial jets flying around the world and compared them to clocks left on the ground. When the planes landed, the airborne clocks were ever so slightly behind. The difference was tiny, just a few hundred billionths of a second, but it confirmed Einstein's prediction. The faster you move, the slower time passes for you. The twin paradox takes this to the extreme. At speeds approaching light, time doesn't just crawl, it nearly stops. For the astronaut twin, a 2-year journey might feel like just that, 2 years. But back on Earth, centuries could have passed. The effect happens because space and time are so deeply intertwined that motion through one directly affects the other. The faster you travel through space, the slower you move through time, like a cosmic trade-off written into the fabric of reality. Here's the real mind bender. It's not an illusion or a trick of perception. Time itself is stretching. If the traveling twin could look back at Earth during their high-speed voyage, they'd see life unfolding in fast-forward, people aging, cities rising and falling, all in a blur. Meanwhile, from Earth's perspective, the astronaut appears frozen in time, barely moving inside their spacecraft. Both experiences are equally real, yet completely out of sync. This paradox forces us to abandon the idea of a universal clock ticking at the same rate for everyone. Time is personal, shaped by how fast you're moving and how strong gravity is around you. And while we don't yet have spaceships that can travel at light speed, the twin paradox isn't just a far-off hypothetical, it's a fundamental feature of our universe, confirmed by everything from jet-borne atomic clocks to the behavior of particles in giant accelerators. So the next time you feel like time is flying by, just remember, it's all relative, literally. What if you could step through a cosmic doorway and emerge light years away in an instant? That's the tantalizing promise of wormholes, hypothetical tunnels in the fabric of space-time that could connect distant points in the universe like shortcuts through folded paper. Think of space-time as a vast sheet and imagine pinching two far apart sections together. A wormhole would be the bridge between them, a shortcut bypassing the enormous distance you'd normally have to travel. While they sound like pure science fiction, think Interstellar's gargantua wormholes aren't forbidden by physics. In fact, Einstein's equations of general relativity suggest they could exist. But here's the catch: wormholes, if real, would be incredibly unstable. Picture a tunnel made of soap bubbles collapsing the moment you try to pass through. According to theory, these cosmic shortcuts would require exotic matter, a mysterious substance with negative energy, to prop them open long enough for anything to traverse them. Exotic matter isn't just rare, it defies normal physics, pushing against gravity instead of being pulled by it. And while we've glimpsed hints of similar phenomena in quantum experiments, we're light years away from harvesting enough to stabilize a wormhole. Even if we could, survival would be another challenge. The gravitational forces inside a wormhole would likely shred anything entering it, stretching atoms into spaghetti like a black hole's tidal forces. Some models suggest only microscopic wormholes could exist naturally, threading the universe like invisible cosmic threads too tiny for even a single atom to pass. Others propose that advanced civilizations, if they exist, might engineer larger ones, forging interstellar highways across the cosmos, the wildest part. Wormholes might not just bridge space, they could bridge time. Traversing one end might send you not just to another location, but to another era entirely. This raises paradoxes that make physicists' heads spin, like the infamous grandfather paradox, where traveling back in time could erase your own existence. Yet despite the hurdles, wormholes remain one of the most thrilling what-ifs in physics. They remind us that the universe's rulebook is still being written, and somewhere in its pages the stars might be closer than they seem. Black holes aren't just cosmic vacuum cleaners, they're nature's ultimate space-time wrecking balls. Imagine the trampoline from earlier, but now replace the bowling ball with a lead weight so dense it punches a hole straight through the fabric. That's a black hole's gravitational grip, so overpowering that not even light can escape once it crosses the event horizon, the point of no return. But the real magic, or nightmare, happens to time itself. As you inch closer to that boundary, seconds stretch into eternity. A clock falling toward the event horizon would appear to tick slower and slower to an outside observer, grinding to a near halt like a movie stuck on pause. This isn't just theory. Picture the protagonist in Interstellar descending toward Gargantua, the film's fictional supermassive black hole. For every hour he spends near the event horizon, 7 years pass on Earth. That gut-wrenching moment when he returns to find his daughter has aged decades, that's gravitational time dilation cranked up to 11. And while the movie takes artistic liberties, the science behind it is shockingly real. Near a black hole's edge, space-time isn't just bent. It's broken, twisted into a one-way street where the future points inexorably toward the singularity at its core. What makes black holes so brutal isn't just their mass, it's their concentration. Take a star 10 times heavier than our Sun and crush it into a sphere the size of New York City. The result, a gravitational field so intense it shreds the rules of physics as we know them. Even light, the fastest thing in the universe, gets dragged back like a car trying to escape a tornado. But here's the cosmic irony. While time screeches to a halt for someone hovering near the event horizon, from their perspective, nothing seems amiss. They'd still feel their watch ticking normally until, of course, they're ripped apart atom by atom in a process physicists cheerfully call spaghettification. Yet black holes aren't just destructive, they're also cosmic laboratories revealing how space-time behaves under extreme conditions. When two black holes collide, they don't just merge, they send ripples through the fabric of space-time itself, the gravitational waves we detected in 2015. These waves are like fingerprints encoding secrets about the black hole's masses, spins, and even the nature of space-time's elasticity. And while we've never directly seen an event horizon, Projects like the Event Horizon Telescope have given us blurry but groundbreaking images of black holes, shadows, dark silhouettes against the glow of superheated gas, a visual testament to space-time's ultimate surrender. So next time you gaze at a seemingly empty patch of sky, remember, somewhere out there, invisible monsters are lurking, bending the universe to their will. They're proof that space-time isn't just a stage, it's a living, breathing entity, warped beyond recognition in places we're only beginning to understand. And if that doesn't make you feel tiny in the grand cosmic scheme, well, just wait until you hear about white holes. Here's something that will bend your brain. The universe is expanding faster than light can chase it. Wait, how is that possible? Doesn't Einstein's famous rule say nothing can outpace light? Well, here's the twist. While nothing can travel through space faster than light, space itself has no speed limit. Think of it like a cosmic treadmill. You could sprint as fast as you want, but if the treadmill beneath you is speeding up even faster, you'll never reach the edge. That's exactly what's happening on a galactic scale. The farther away a galaxy is, the faster it appears to race away from us, not because it's moving through space, but because the fabric of space between us is stretching. At some point, that expansion hits warp speed, carrying galaxies beyond what we call the cosmic horizon. It's like watching a ship vanish over the curve of the ocean, except this time there's no telescope powerful enough to bring it back. Light from those distant galaxies can't reach us anymore because the space between us is growing faster than the light can cross it. They're not just far, they're gone, locked away by the universe's own expansion. This isn't some distant future scenario, it's happening right now. Take a galaxy billions of light years away, and by the time its light finally reaches us, the space it's traversing has stretched so much that the light gets redder, weaker, stretched into oblivion like a cosmic rubber band. Eventually, even the most powerful telescopes will see nothing but darkness where vibrant galaxies once shone. Future astronomers might peer into the sky and find only our local galactic neighborhood, with no clue that a vast, invisible ocean of stars once surrounded us. The craziest part, this expansion is accelerating. Scientists discovered this in the late 1990s by studying supernova, stellar explosions that serve as cosmic yardsticks. The data revealed that some mysterious force, nicknamed dark energy, is pushing the universe apart faster and faster. It's as if the treadmill suddenly cranked up to hyperspeed. If this keeps up, billions of years from now, the universe could become a lonely, fragmented place with galaxies isolated in their own pockets of space, unaware of one another's existence. So yes, light speed is the universe's ultimate speed limit for anything traveling within space. But space itself, it plays by its own rules, stretching faster than light can keep up, rewriting the map of the cosmos in real time. And that means the universe we see today is just a fleeting snapshot, a single frame in an ever-expanding cosmic film where most of the action is already slipping out of view. What if time isn't a flowing river but a frozen ocean where past, present, and future exist simultaneously, laid out like frames on an endless film reel? This is the spine-tingling idea behind the block universe theory, a concept that turns our everyday experience of time on its head. In this view, the universe isn't a series of moments unfolding one after another. It's a static, four-dimensional block where every event that ever was or will be simply is, fixed in place like landmarks on an unchanging map. Your birth, your first step on the moon, if humanity ever gets there, and the heat death of the universe trillions of years from now all exist with equal reality, just in different coordinates of space-time. Einstein himself hinted at this when he wrote, "The distinction between past, present, and future is only a stubbornly persistent illusion. Think of it like a DVD." The movie's entire plot, the opening scene, the climax, the credits is already encoded on the disc. When you hit play, your consciousness is like the laser moving through the frames, experiencing time sequentially even though every moment is technically always there. This isn't just philosophical musing. The equations of relativity treat time as just another dimension, no more special than up, down, or sideways. Gravity bends it, motion stretches it, but nowhere do the laws of physics say it has to flow. So why does time feel so relentless? Some scientists argue it's all about entropy, the universe's tendency toward disorder. Imagine a shattered vase. You instantly know whether the video of it breaking is playing forward or backward because entropy only increases in one direction. Our brains might use this cosmic arrow of disorder to stitch together the illusion of a moving now. But in the block universe, that's just how we perceive the slice of reality we're currently passing through. The implications are dizzying. Free will starts to feel like a mirage. If the future is already out there, are we just passengers reading lines from a cosmic script? Not necessarily. Some interpretations suggest the block universe is more like a branching tree, with every possible decision creating new timelines. Others propose that consciousness itself stitches together the illusion of time, like a projector weaving still images into motion. One thing's certain, time's grip on reality is far looser than we ever imagined. So the next time you check your watch, remember those ticking seconds might just be a trick of the mind, a fleeting shadow cast by a universe where everything is already written in the stars. Einstein called it spooky action at a distance, a phenomenon so bizarre it made even the father of relativity uneasy. Quantum entanglement defies everything we know about space-time, creating a cosmic connection between particles that transcends distance, speed, and even logic. Here's how it works. Take two particles and entangle them, linking their properties like cosmic twins. From that moment on, no matter how far apart they're separated, whether by a millimeter or a galaxy measuring one, instantly determines the state of the other. Not at the speed of light, not after a delay, but immediately, as if space-time doesn't apply to them. Imagine tossing a pair of gloves into separate black holes billions of light years apart. Open one box and find a left-handed glove, and you'd instantly know the other holds a right-handed one, no signal needed. That's the essence of entanglement. It's as if the universe has a hidden hotline bypassing the cosmic speed limit, binding particles in a way that looks like magic but operates under cold, hard quantum law. Here's where it gets even weirder. This connection doesn't rely on any known force or particle shooting between them. It's not a cosmic thread or a wave. It's a fundamental property of quantum mechanics where the particles exist in a shared state until observed. Measure one and the other snaps into place like a mirror image, no matter how vast the distance. Experiments have confirmed this again and again, with particles separated by over 1,000 kilometers still behaving as one. The implications rip through our understanding of reality. If entangled particles communicate faster than light, does that violate relativity? Not exactly. While the correlation is instant, no actual information or energy is transmitted. It's as if the universe pre-loaded the particles with synchronized instructions, revealing the link only when we peak. Still, this spooky effect hints that space-time might be a surface layer over a deeper, stranger quantum reality, one where separation is an illusion and everything is fundamentally interconnected. Some theories suggest entanglement could be the foundation for future technologies like quantum teleportation or unhackable communication networks. Others wonder if it's a clue to space-time's true nature, that what we perceive as empty vacuum might be seething with invisible quantum connections, stitching the cosmos together like hidden stitches in fabric. Either way, entanglement proves that beneath the calm surface of space-time, the universe is playing a game we're only just beginning to understand. The Big Bang wasn't just an explosion, it was the moment space and time themselves burst into existence. Imagine trying to rewind the universe like a cosmic film reel. Galaxies rush closer together, stars vanish into collapsing clouds of gas, temperatures skyrocket. Keep rewinding and you'd eventually reach a point where everything, all matter, energy, even the dimensions we take for granted, was compressed into a single, unfathomably dense speck, a singularity. Not a tiny ball in space, but a point of space-time where the very concepts of before and outside lose all meaning. This is the mind-shattering truth about the Big Bang. It wasn't just the birth of stars and planets, it was the birth of reality's stage itself. Time didn't tick here because there was no here to measure. Space didn't stretch because there was no there to expand. The singularity wasn't floating in some void. It was the entirety of existence, a cosmic seed containing all the potential of the universe. Then, in a fraction of a second, space-time unfurled like a flower blooming at infinite speed, carrying matter and energy outward in a fireball so hot it could forge atoms from pure energy. But here's where physics hits a wall. If space and time began at the Big Bang, asking what came before is like asking what's north of the North Pole. Without time, there's no before. Without space, there's no where. Some theories, like quantum loop gravity, suggest time might have existed in a different form, a foamy, fluctuating state where cause and effect break down. Others propose our universe is just one bubble in an endless multiverse, with new space-times sprouting eternally. The most haunting question: what ignited the Big Bang in the first place? Was it a random quantum fluctuation, a collision of higher dimensional membranes, or something beyond our comprehension? For now, the answers lie shrouded in the singularity's shadow, a reminder that the universe's greatest origin story is still missing its first page. And that mystery, what happened when there was no when, no where, just a flicker of potential, might be the most astonishing fact of all. Time travel to the future isn't just science fiction, it's a guaranteed feature of Einstein's universe, and we've already proven it works. Picture an astronaut launching into space at near light speeds. While their journey might feel like a few years, decades or even centuries could pass on Earth by the time they return. This isn't hypothetical. Astronauts on the International Space Station experience it on a tiny scale. Because they're moving faster than everyone on the ground, their clocks tick ever so slightly slower. Over months in orbit, they've technically time-traveled a fraction of a second into the future. Crank up the speed and the effect becomes dramatic. At 99% light speed, a 5-year trip for the astronaut could mean 36 years back home. Stephen Hawking once tested this idea with a cheeky experiment. In 2009, he threw a party for time travelers, but here's the catch: he only sent out invitations after the event. His logic: if future humans ever invent time machines, they'd know to show up. The room stayed empty. While that might seem like proof time travel is impossible, it actually reveals something deeper. If hopping to the past is a paradox minefield, traveling to the future is unavoidable. Every moment, we're all sliding into the future at different rates, just usually too subtly to notice. Gravity does the same trick as speed. Near a black hole's event horizon, where space-time warps into a steep well, time slows to a crawl relative to the outside universe. A single orbit around the black hole could spit you out centuries later, like hitting pause on Earth's clock. This is the real science behind Interstellar's heart-wrenching scenes, where hours for the crew equal decades for those waiting. And while we don't have black holes handy for testing, atomic clocks prove the effect exists even on Earth. Place one at sea level and another on a mountain where gravity is weaker and the higher clock runs faster. Over time, they drift out of sync, so why haven't we built a time machine yet? The problem isn't the physics, it's the engineering. To reach meaningful time dilation, you'd need speeds or gravitational forces beyond our current technology. Even a one-way trip to the future would require surviving accelerations that would turn a human body into jelly. But the universe doesn't care about our technical limitations. Somewhere out there, stars or black holes are bending time into pretzels, proving the future isn't a fixed destination. It's a destination you can race toward if you're bold enough to ride the extremes of space-time. Why does time only move forward? The answer might lie in something as ordinary as a dropped glass shattering on the floor. Watch it break, and you instantly know the footage isn't playing backward, because in our universe, disorder always increases. This irreversible slide toward chaos is called entropy, and it's the hidden force behind time's one-way arrow. Think of entropy as nature's ultimate prankster, constantly scrambling the universe into messier arrangements. When you mix cream into coffee, it doesn't spontaneously unmix. When a sandcastle collapses, it doesn't rebuild itself. These everyday moments reveal a cosmic rule. Systems evolve from order to disorder, never the reverse. That's why we remember the past but not the future, because entropy leaves a trail of breadcrumbs in one direction only. Here's where it gets profound. At the quantum level, particles don't care about time's direction. Flip the equations of physics and they work just as well backward. So why does the macroscopic world stubbornly march forward? Entropy provides the missing link. Imagine a deck of cards perfectly stacked in order by suit and number. Shuffle it once and it's slightly disordered. Keep shuffling and the chances of it ever returning to its original state become vanishingly small. The universe works the same way, starting with a highly ordered state, the Big Bang's unimaginably dense energy. It's been shuffling outward for 13.8 billion years, spreading into ever more probable and disordered configurations. This explains why we can't unbreak an egg or unburn a log. Those processes scatter energy and matter into trillions of unpredictable states, making reversal statistically impossible. Even if every particle in the shattered glass spontaneously reversed its motion, a vanishingly unlikely event, it still wouldn't truly unshatter, because heat and sound energy would have already dissipated into the environment, lost to the universe's growing entropy pool. The eerie consequence: time's arrow might be an illusion born from perspective. If the universe began in a low entropy state, our perception of time flowing forward could just be us riding the entropy wave toward equilibrium. Some theories suggest that if entropy ever maxed out, a hypothetical heat death, where energy is evenly spread, time as we know it would lose all meaning, with no direction left to point. So next time you see spilled milk, don't cry over it, marvel at it. That mess is a tiny piece of a cosmic countdown, a reminder that the universe is playing a one-way game and we're all just along for the ride. Every cracked window, every rusted hinge, every breath you exhale into the air is another tick of entropy's clock, etching the irreversible passage of time into the fabric of reality itself. Imagine the universe as a loaf of raisin bread baking in an oven, except this loaf never stops expanding, and the raisin's galaxies keep getting farther apart at an ever-increasing speed. That's the eerie reality we live in, thanks to a mysterious force called dark energy. Unlike gravity, which pulls cosmic objects together, dark energy does the opposite. It pushes space-time apart with a repulsive force so powerful it's accelerating the expansion of the entire universe. Scientists discovered this in the late 1990s when they observed distant supernova glowing dimmer than expected, revealing that the space between galaxies wasn't just growing, it was stretching faster and faster over time. Here's where it gets unsettling. If dark energy's push continues unchecked, it won't just separate galaxies, it could shred the very fabric of reality. Picture a rubber band stretched so thin it snaps. Now apply that to space-time itself. In a scenario cosmologists call the Big Rip, dark energy's repulsive force would eventually overcome all other forces in the universe. First, galaxy clusters would tear apart as the space between them expands too rapidly for gravity to hold them together. Next, individual galaxies would unravel, stars ripped from their orbits. Then, as the acceleration reaches nightmarish levels, planetary systems would disintegrate. In the final moments, even atoms, the building blocks of matter, would be torn asunder, their nuclei unable to withstand the stretching of space itself. Time as we know it would cease to have meaning in a universe where nothing can hold together. The timeline for this cosmic doomsday depends on dark energy's strength, a number scientists are still racing to pin down. Some models suggest the Big Rip could happen in as little as 22 billion years. Others argue dark energy might weaken over time, sparing the universe from total disintegration. But here's the twist: even if the Big Rip never occurs, dark energy's grip guarantees a lonelier cosmos. Billions of years from now, galaxies beyond our local group will vanish over the cosmic horizon, their light stretched beyond detectability. Future civilizations might gaze at a night sky nearly empty of stars, unaware that a vast universe once teemed beyond their isolated pocket of space. Yet dark energy isn't just a destroyer, it's also one of the greatest puzzles in physics. What is it? The leading theory suggests it's the energy of empty space itself, a property of the quantum vacuum that permeates the universe. But when physicists calculate how much energy the vacuum should have, their numbers are off by a staggering factor of 10 to the power of 120. That's like predicting a cup of coffee should boil the Pacific Ocean, only to find it can't even warm a teaspoon. This cosmological constant problem hints that we're missing something fundamental about how space, time, and energy intertwine. For now, dark energy remains a cosmic wild card, its true nature hidden in the shadows of our equations. Whether it leads to a silent fade or a violent end, one thing's certain: the universe is playing by rules we've only begun to decipher, and the ultimate fate of space-time hangs in the balance. Gravitational waves are the universe's way of sending shock waves through space-time itself, ripples that stretch and squeeze the very fabric of reality. These aren't gentle undulations like waves on a pond. They're cosmic tsunamis born from the most violent events in existence: black holes colliding, neutron stars spiraling into each other, and the universe's very birth echoing through the cosmos. Until recently, they existed only in Einstein's equations, a prediction so faint scientists doubted we'd ever detect them. Then, in 2015, a breakthrough shook the scientific world. The Laser Interferometer Gravitational Wave Observatory, or LIGO, caught the unmistakable signature of two black holes merging over 1 billion light-years away. Imagine two voids, each dozens of times heavier than our Sun, locked in a death spiral. As they circled closer, they warped space-time around them, sending out ripples at the speed of light. By the time they crashed together, the energy released was so immense it momentarily outshone every star in the observable universe, all channeled into vibrating the fabric of space itself. LIGO lasers, bouncing down miles-long tunnels, detected a distortion smaller than a fraction of an atom's width as the wave passed through Earth. What's astonishing isn't just the detection, it's what these waves sound like. Scientists can convert the ripples into audio, translating space-time's vibrations into sound. The result, a cosmic chirp, a fleeting crescendo that rises in pitch as the black holes whirl faster, then cuts off abruptly at the moment of collision. It's as if space-time is a drumhead, and these cataclysmic events are the drumsticks. Each collision has its own unique tone. Neutron stars create a higher-pitched ring, while supermassive black holes produce a deep, resonant thud. But gravitational waves aren't just echoes of destruction. They're a new way to see the universe. Light can be blocked or bent, but space-time ripples pass through everything, carrying unfiltered information from the darkest corners of existence. They've already revealed black holes of unexpected sizes, confirmed Einstein's predictions with razor-sharp precision, and even offered clues about the nature of gravity itself. In a way, we've been deaf to the cosmos until now, and LIGO detections are the first notes in a symphony we're only beginning to hear. This discovery didn't just open a window, it tore open a new dimension of astronomy. Future detectors like the space-based LISA mission could catch waves from the universe's earliest moments, whispers from a time before stars or galaxies existed. We might even detect echoes of cosmic strings, hypothetical defects in space-time left over from the Big Bang. gravitational waves remind us that space isn't empty and silent. It's a dynamic, ever-vibrating arena where even the quietest events like the death dance of two invisible black holes can send tremors across the cosmos. Here's an unsettling thought. What if your entire existence flashed by in an instant with no sense of time passing at all? That's the bizarre reality for a photon, a particle of light hurtling through the cosmos at the universe's speed limit. According to Einstein's relativity, the faster you move through space, the slower you move through time. But light doesn't just move fast, it travels at the maximum speed possible, where time doesn't just slow down, it stops. For a photon, the moment it's emitted from a star or a flashlight is the same moment it's absorbed by your eye or a distant planet. Its entire journey, whether a nanosecond across a lab or billions of years across the universe, is over in a blink, literally. Picture this: a photon leaves the surface of the Sun, streaking toward Earth at nearly 300,000 kilometers per second. From our perspective, that trip takes around 8 minutes. But from the photon's point of view, no time passes at all. It doesn't experience the 8-minute journey or even the tiniest fraction of it. The Sun's surface and your retina exist at the same instant in its frame of reference. This isn't just theoretical wordplay. Atomic clocks on fast-moving jets confirm time dilation, ticking slower than their stationary counterparts. Push that speed to light speed and the clock would stop entirely. This leads to some mind-bending conclusions. If a photon could think, its entire existence from the Big Bang's first light to the glow of your phone screen would be a single frozen moment. Stars, galaxies, and cosmic history would flicker by like a slideshow with no duration. The universe, as we perceive it unfolding over eons, would feel like a static snapshot. Even stranger, from light's perspective, the universe has no thickness. Space itself contracts to zero length along its path, compressing the vast cosmos into an infinitesimal point. Yet light doesn't experience any of this. It doesn't experience at all. No aging, no decay, no sense of waiting, just an eternal now stretched across space-time. This reveals something profound. Time isn't just flexible. At the extremes, it can vanish, leaving behind a frozen reality where cause and effect collapse into a single instant. The next time you flick on a light switch, remember those photons didn't travel to you. From their viewpoint, they were already there, waiting in the darkness for you to press the button. What if our universe isn't the only one? Imagine a cosmic foam, bubbling with countless other realities, each a separate universe with its own rules, its own history, even its own version of you. This isn't science fiction, it's a serious possibility in modern physics known as the multiverse. According to theories like inflationary cosmology, the Big Bang might not have been a one-time event. Instead, space-time could be endlessly spawning new universes like bubbles in a boiling kettle, each inflating rapidly into its own isolated cosmos. Some of these bubble universes might have physics entirely alien to ours, where gravity repels instead of attracts, where time runs backward, or where light travels at a different speed. Take Schrödinger's famous cat, trapped in a box where it's simultaneously alive and dead until someone looks inside. Quantum mechanics suggests all possible outcomes exist until observation collapses them into one. Now scale that up to the universe. What if every quantum decision, every particle spin, every atomic interaction branches off a new reality? In this many worlds interpretation, there's a universe where dinosaurs never went extinct, where you took that job offer you declined, or where the laws of space-time let stars form in perfect geometric shapes. String theory adds another layer of weirdness. It proposes that our universe might just be one membrane floating in a higher dimensional space, occasionally bumping into others. These collisions could trigger new Big Bangs, or even explain mysterious cosmic anomalies like the infamous cold spot in our universe's background radiation, which some speculate might be a bruise from a long-ago clash with another reality. The wildest part, we might never see these parallel universes. If they're tucked beyond our cosmic horizon, forever receding faster than light can bridge the gap, they'd be as unreachable as a shadow on a distant wall. Yet their potential existence reshapes how we think about space-time's flexibility. If the multiverse is real, then our universe isn't the stage. It's just one theater in an endless cosmic multiplex, each running a different show with different rules. And that means the mysteries we're unraveling about black holes, dark energy, and time itself might only be local bylaws in a much grander, stranger cosmos. What if the three-dimensional world we experience is nothing more than an illusion, a holographic projection encoded on a distant two-dimensional surface? This is the radical idea behind the holographic principle, a concept so strange it blurs the line between science and science fiction. Picture a credit card hologram, tilt it, and a flat, shiny surface suddenly appears to have depth with images that seem to pop out in 3 dimensions. Now imagine the entire universe working the same way, every galaxy, every planet, even the chair you're sitting on, all just incredibly detailed projections from information written on the cosmic equivalent of a flat, two-dimensional screen at the edge of reality. This isn't just wild speculation. The holographic principle emerged from a burning question in physics: what happens to information that falls into a black hole? According to quantum mechanics, information can never truly be destroyed. It might get scrambled, but it can't vanish without a trace. But black holes seem to break this rule. Once something crosses the event horizon, it's gone forever, leaving no way to recover the data it carried. This contradiction, known as the black hole information paradox, has troubled physicists for decades. Enter the holographic principle. In the 1990s, scientists discovered something astonishing. The amount of information a black hole can hold isn't proportional to its volume, as you'd expect, but to its surface area, the two-dimensional boundary of its event horizon. It's as if all the data about what's inside the black hole is somehow painted on its surface like a cosmic barcode. This led to a jaw-dropping realization. If a black hole's interior can be fully described by information on its boundary, maybe the entire universe can too. Think of it like a video game. The lush, three-dimensional world you explore isn't actually rendered in full detail everywhere at once. It's generated on the fly based on data stored in simpler, two-dimensional code. The holographic principle suggests reality might work the same way. The world we see, with its mountains, oceans, and stars, could be a kind of cosmic render, projected from fundamental bits of information etched on the universe's outer edge, a place we'll never see or reach. The implications are staggering. If the holographic principle is true, space-time isn't the fundamental fabric of reality. It's an emergent phenomenon, like the surface of a pond emerging from countless water molecules. This could solve the black hole paradox. Information isn't lost inside the singularity. It's preserved on the event horizon like a celestial hard drive. Even stranger, it hints that the universe might not need 3 spatial dimensions to exist in the way we experience. The true reality could be a vast, flat informationscape, with our 3D world unfolding as a kind of grand illusion. Experiments are already testing this mind-bending idea. Precision measurements of cosmic microwave background radiation, the afterglow of the Big Bang, have searched for telltale pixelation in space-time, tiny irregularities that might betray its holographic nature. So far, no smoking gun, but the search continues. Whether the holographic principle holds up or not, it's a thrilling reminder that the universe's deepest truths might be hiding in plain sight, written not in the language of space and time, but in the cryptic code of information itself. If black holes are the universe's ultimate eaters, sucking in everything that crosses their path, then white holes would be their exact opposite, cosmic fountains spewing out matter and energy in an unstoppable eruption. Imagine hitting rewind on a black hole's life cycle. Instead of collapsing inward, a white hole violently explodes outward, refusing to let anything enter its event horizon. It's like a one-way door where matter can only exit, never return. These bizarre objects aren't just science fiction. They emerge as legitimate solutions to Einstein's equations of general relativity, the same math that predicts black holes. But while black holes have been observed indirectly for decades, white holes remain purely theoretical ghosts in the machinery of space-time, tantalizing but elusive. Think of a white hole as a black hole's time-reversed twin. If you filmed a black hole sucking in a star and then played the footage backward, you'd see something resembling a white hole, a sudden, bright outburst of material from a central point. But here's the catch: white holes aren't just black holes running in reverse. They're their own independent phenomena with one key difference. They violate the second law of thermodynamics, the rule that says entropy or disorder always increases over time. A white hole would essentially be a cosmic reset button, ejecting perfectly ordered matter and energy into the universe like a shaken soda can bursting open. That's why many physicists argue they can't exist in reality. Nature prefers messiness over perfection. Yet the math doesn't rule them out entirely. Some theories suggest white holes could be the other end of black hole tunnels, wormholes bridging distant points in space-time. Picture a black hole swallowing matter in one corner of the universe, only for a white hole to vomit it out somewhere else or even in another time entirely. Others propose that white holes could explain mysterious cosmic explosions like gamma-ray bursts, the most energetic event since the Big Bang. If a dying black hole somehow bounced into a white hole, it might unleash a cataclysmic burst of energy visible across the universe. Then there's the wildest idea of all, that our own Big Bang might have been a white hole event. Think about it. A singularity suddenly disgorging all the matter and energy of the cosmos in an irreversible outburst. It's a poetic twist, suggesting that every black hole in our universe could someday blossom into a white hole in another, birthing a new reality from the ashes of an old one. For now, white holes remain one of physics' most intriguing what-ifs. No telescope has ever spotted one, and their existence would rewrite some of our deepest assumptions about time and entropy. But in a universe where space-time can warp, twist, and even holographically project reality, who's to say cosmic fountains aren't hiding somewhere in the dark, waiting to rewrite the rules? Time crystals sound like something straight out of a sci-fi novel, structures that move in a repeating cycle forever without ever losing energy. These aren't just theoretical curiosities, they're real, experimentally confirmed phases of matter that break one of physics' most fundamental assumptions, the symmetry of time. Normally, if you watch a physical system like a swinging pendulum or a bouncing ball, it'll eventually slow down and stop as energy dissipates. But time crystals laugh at this rule. They're like a pendulum that keeps swinging perfectly without any pushes, defying the universe's relentless slide toward entropy. The idea was first proposed in 2012 by Nobel laureate Frank Wilczek, who wondered, could there be a form of matter that's perpetually in motion, not because it's gaining energy, but because its ground state, its lowest energy configuration, is inherently dynamic? Imagine a clock that ticks forever without winding, or a ring of atoms that flips its spin back and forth eternally, locked in a rhythm that doesn't decay. At first, many physicists dismissed the concept as impossible, arguing it violated the laws of thermodynamics. But by 2017, two separate teams had created time crystals in the lab using chains of ytterbium ions and diamond defects, proving Wilczek right. Here's the catch: time crystals don't violate the laws of physics, they reinterpret them. They achieve their endless motion not by creating energy from nothing, but by existing in a quantum state where their particles are entangled in a way that resists equilibrium. Think of it like a dance where every atom knows its steps perfectly, forever out of sync with the music but never missing a beat. Unlike ordinary crystals, which repeat their structure in space like the lattice of a diamond, time crystals repeat their structure in time, oscillating at a fixed frequency even in their lowest energy state. What makes them even stranger is their relationship with time symmetry. Most physical processes look the same whether time runs forward or backward. A video of a swinging pendulum makes sense played in reverse. But time crystals break this symmetry. Their oscillations have a preferred direction, like a metronome that only ticks left to right, never right to left. This makes them the first known examples of non-equilibrium matter, a new phase that exists outside the old categories of solid, liquid, or gas. Practical applications. They're still speculative, but time crystals could revolutionize quantum computing. Their stable, self-repeating states might serve as perfect quantum memory, immune to the decoherence that plagues current qubits. Or they could help simulate exotic physics like the behavior of matter near black holes. For now, though, they're mostly a breathtaking reminder of how much we still don't understand about time, equilibrium, and the hidden rhythms woven into the fabric of reality. The universe, it seems, still has a few magic tricks up its sleeve, and time crystals are one of its most dazzling. The Fermi paradox poses a haunting question. If the universe is so vast and ancient, teeming with billions of potentially habitable planets, why does it feel so empty? One unsettling possibility is that advanced civilizations aren't just hiding, they've mastered the fabric of space-time itself, slipping through cosmic backdoors we haven't even begun to map. Imagine a civilization millions of years ahead of us, no longer bound by the sluggish pace of rocket travel. Instead of crossing the immense voids between stars, they might fold space like origami, using wormholes or warped regions of space-time as shortcuts. To them, our frantic searches for radio signals or planetary biosignatures might seem quaint, like sending smoke signals to a society with smartphones. Think of it like this: if humanity ever perfects warp drives or traversable wormholes, would we still broadcast our presence to the cosmos, or would we become invisible by default? Advanced civilizations might operate in dimensions or scales we can't perceive, their infrastructure hidden in the quantum foam of space-time or tucked inside microscopic black holes. They could be harvesting energy from singularities, communicating via entangled particles, or even altering the flow of time to optimize their existence, rendering traditional astronomy blind to their presence. Then there's the darker twist. What if the great filter, the hypothetical barrier preventing civilizations from reaching interstellar scales, isn't behind us but ahead? Space-time itself could be a minefield. Wormholes might destabilize and collapse, erasing travelers. Artificial black holes could spiral out of control. Or worse, exploiting space-time might attract cosmic predators, incentivizing advanced societies to cloak themselves in perfect silence. The absence of aliens might not be an accident. It could be the ultimate survival strategy in a universe where the real monsters aren't extraterrestrials, but the laws of physics themselves. Yet there's a sliver of hope. If civilizations are manipulating space-time, we might catch glimpses in the data. Unexplained gravitational waves, bizarre quantum fluctuations, or even anomalies in cosmic expansion could be the fingerprints of their engineering. Until then, the silence of the cosmos remains either a chilling warning or an invitation to dig deeper into the mysteries of space-time, where the answers to Fermi's question might be hiding in plain sight. The universe as we know it could vanish in an instant, not with a bang, but with a whisper. Hidden in the seemingly empty void of space lies a terrifying possibility: vacuum decay. Picture the fabric of reality like a frozen lake on a warm spring day. Right now, we're skating on solid ice, our universe's current laws of physics holding firm. But beneath that stable surface, there might be a deeper, more fundamental state of reality, like water waiting to melt the ice away. If even a single point in space-time were to tunnel into this lower energy state, it could trigger a cataclysmic chain reaction. a bubble of new physics expanding at the speed of light, rewriting the rules of existence as it grows. This isn't just speculative doom-mongering. The concept stems from how we understand quantum fields, the invisible scaffolding that underpins everything in the universe. These fields hum with energy, and right now, they're in what we call a false vacuum, a stable but not perfectly stable state, like a marble resting in a shallow bowl. It's holding for now, but if something jostled that marble hard enough, say, a high-energy particle collision or a random quantum fluctuation, it could roll into a deeper valley, a true vacuum. The moment that happens, the laws of physics inside that bubble would change instantly, and the bubble's walls would surge outward, unstoppable. Inside this expanding sphere of annihilation, atoms might not hold together. Gravity could invert, light might not even travel the same way. The new laws would be utterly alien, determined by whatever lower energy state the quantum field settled into. And because the bubble moves at light speed, we'd never see it coming. One moment, everything's normal. The next, the edge of the bubble hits Earth, and reality as we know it simply stops. The good news, if it hasn't happened in 13.8 billion years, it's probably rare. The bad news, it could already be on its way. A vacuum decay event might have triggered in some distant galaxy, and its wave of obliteration could be halfway here. We'd have no warning, no defense, but here's the strangest twist. If the new physics inside the bubble allowed for any form of life or consciousness at all, the beings born there would never know the old universe existed. To them, their reality would always have been the default, a chilling reminder that the cosmos might not just change but forget its own past entirely. So is vacuum decay a lurking cosmic doomsday, or just a fascinating thought experiment? Until we understand quantum fields more deeply, we won't know for sure. But it's a humbling reminder. The universe's rules aren't just mysterious, they might be provisional, waiting for a quantum sneeze to rewrite them all. Loop quantum gravity dares to rewrite Einstein's cosmic rulebook with a bold proposition. What if space-time isn't smooth and continuous, but built from minuscule, indivisible grain? Picture the universe as an intricate tapestry, woven not from endless fabric, but from countless microscopic threads. These atoms of space-time, tiny, vibrating loops, would be the smallest possible units of reality, far tinier than an atom's nucleus. Unlike string theory's floating filaments in higher dimensions, loop quantum gravity grounds itself in the tangible, suggesting space itself has a pixelated structure when you zoom in close enough. This granularity isn't just a curiosity, it could solve one of physics' greatest headaches, the crushing infinities of singularities inside black holes. At the heart of this theory lies a radical idea: space can't be divided infinitely. Just as you can't split an atom beyond its fundamental particles, space-time might have a limit to how finely it can be sliced. These tiny loops, interconnected like a cosmic mesh, would define the very fabric of existence. The math reveals something astonishing. When matter gets compressed to extreme densities, like in a black hole's core, the loops resist further collapse. Instead of a singularity, a point of infinite density where space-time curves endlessly, you'd hit a bounce. The collapse reverses like a spring recoiling, potentially birthing a new region of space-time. This could mean black holes aren't cosmic dead ends, but portals to something entirely unexpected. The implications ripple outward. If space-time is granular, the Big Bang might not have been a true singularity either. Instead of an infinitely dense starting point, the universe could have emerged from a prior contraction, a big bounce, where an older cosmos collapsed before rebounding into our own. This erases the need for a definitive beginning, offering an elegant alternative to the singularity's paradox. Even time in this framework isn't continuous. It flows in discrete steps like frames in a movie reel, though so rapid we'd never perceive the flicker. But how do we test such a wild idea? The answer might lie in the cosmos' faintest whispers. If space-time has a granular structure, ultra-high-energy particles like cosmic rays could interact with it subtly, leaving detectable fingerprints in their behavior. Some physicists speculate that gamma-ray bursts, the universe's most energetic explosions, might carry distortions caused by bumping against space-time's tiny loops. Others hunt for anomalies in gravitational waves, hints of quantum graininess echoing from colliding black holes. Loop quantum gravity isn't without rivals, of course. String theory, with its extra dimensions and vibrating strings, dominates much of the conversation. But where string theory seeks to unify all forces by building upward from particles, loop quantum gravity starts with space-time itself, crafting a universe from the ground up. It's a philosophical clash as much as a scientific one. Should we prioritize the stage space-time or the actor's particles? For now, both remain unproven, leaving the true nature of reality hanging in the balance. Yet the allure of loop quantum gravity is undeniable. It offers a universe where nothing, not even space, is infinitely divisible, where black holes might hide secret rebirths, and where the Big Bang was just one chapter in an endless cosmic cycle. It's a reminder that the fabric of reality, no matter how seamless it appears, might yet unravel into something far stranger under scrutiny. And if we ever prove its predictions, we won't just understand space-time better, we'll rewrite the very definition of existence. Here's a thought so unsettling it'll make you question the nature of your own existence. What if you aren't part of an ancient, orderly universe, but just a fleeting glitch in the chaos of space-time? This is the chilling premise of the Boltzmann brain paradox, a cosmic riddle that pits our understanding of reality against the cold, uncaring laws of thermodynamics. Imagine the universe as an endless sea of random fluctuations. Given enough time, trillions upon trillions of years, couldn't the jostling of particles spontaneously arrange themselves into a self-aware mind, complete with false memories of a past that never happened? A brain that, for just an instant, hallucinates an entire cosmos before dissolving back into the void. The paradox takes its name from Ludwig Boltzmann, the 19th century physicist who helped unravel entropy's mysteries. He theorized that given infinite time, even the most improbable events become inevitable, including the random assembly of ordered structures like stars, planets, or consciousness itself. In an eternally expanding universe dominated by entropy, where disorder reigns supreme, the statistics get bizarre. It's far more likely, mathematically speaking, for a single, fully formed brain to pop into existence from quantum noise than for an entire ordered universe like ours to arise purely by chance. After all, constructing one self-aware entity requires infinitely less energy and precision than assembling billions of galaxies, stars, and civilizations. So why do we perceive a coherent, ancient universe instead of blinking into existence as solitary Boltzmann brains? Some argue our very observation of cosmic history, the fossil record, the light from distant stars disproves the idea. But the paradox counters. What if those observations are also illusions, fabricated memories embedded in the brain's fleeting moment of awareness? It's the ultimate solipsistic nightmare, where you can't trust even the evidence against the theory because the evidence itself might be imaginary. Modern physics offers escape routes. Cosmic inflation, the universe's explosive early growth, might have locked in order so thoroughly that Boltzmann brains are statistically suppressed. Or perhaps the multiverse endlessly spawns real universes, making our orderly cosmos one of countless legitimate siblings rather than a mirage. But the paradox lingers like a shadow, reminding us that in an eternal, entropic cosmos, reality's foundations might be shakier than they seem. The next time you gaze at the stars, ask yourself, are you truly a product of 13.8 billion years of cosmic evolution, or just a phantom flicker in the dark, doomed to forget itself as quickly as it appeared? The Big Bang is often billed as the ultimate beginning, a moment when space, time, and the very laws of physics burst into existence. But what if it wasn't the start at all? Imagine a cosmic cycle where universes expand, contract, and rebound endlessly, like a lung breathing in and out across eternity. This is the heart of bouncing cosmology, a theory that dares to ask, could our universe be just the latest chapter in an infinite saga of cosmic rebirth? Picture a black hole's crushing grip taken to the extreme, not just collapsing a star but an entire universe. As space-time contracts toward a singularity, quantum effects might prevent true annihilation. Instead of reaching infinite density, the universe could hit a quantum bounce, where gravitational repulsion overcomes collapse, triggering a new Big Bang. It's like squeezing a spring so tightly it recoils with explosive force, birthing a fresh universe from the ashes of the old. Loop quantum gravity, a leading contender for unifying quantum mechanics and relativity, suggests this could leave detectable imprints, subtle swirls in the cosmic microwave background, faint echoes of a universe that came before ours. Then there's the cyclic model, where our universe exists in an endless dance with a parallel reality. Imagine two sheets of space-time separated by a higher dimension, periodically colliding like symbols. Each collision ignites a new Big Bang, with matter and energy flooding into both universes before they drift apart, cool, and eventually crash together again. These cycles could stretch across trillions of years, each iteration subtly different from the last, like a cosmic phoenix rising and falling in an unbroken loop. But the wildest twist might lie in Roger Penrose's conformal cyclic cosmology, where the distant future of one universe becomes the Big Bang of the next. As black holes evaporate and particles lose mass over eons, the universe might dissolve into a formless sea of radiation, a state mathematically identical to the ultra-smooth, ultra-dense conditions of the Big Bang. In this mind-bending view, the end of time loops back to its beginning, stitching universes together like chapters in an infinite book where the last sentence always reads, "Once upon a time." The evidence: some claim to have spotted circular patterns in the cosmic microwave background, ghostly imprints of black hole collisions from a pre-Big Bang era. Others hunt for gravitational waves from universe-shattering bounces. Whether these theories hold up or not, they shatter the illusion of cosmic uniqueness. If space-time existed before the Big Bang, our universe isn't a solitary creation, it's a single note in an eternal symphony, playing on a stage older than time itself. Hold onto your seats, because the Alcubierre warp drive is about to bend your understanding of space travel into a pretzel. Imagine a starship cruising through the cosmos, not by brute forcing its way forward with rockets, but by cheating the universe's speed limit. Instead of moving through space at light speed, the ship would ride a wave of compressed and expanded space-time, like a surfer gliding on a cosmic ripple. Space in front of the vessel contracts, pulling the destination closer, while space behind expands, pushing the departure point farther away. The ship itself sits in a flat, warp bubble between these distortions, never accelerating locally, meaning it doesn't break Einstein's sacred rule that nothing can travel through space faster than light. This isn't science fiction. Mexican physicist Miguel Alcubierre proposed the idea in 1994, showing mathematically that such a drive fits within general relativity's framework. The catch: it requires something called exotic matter, a hypothetical substance with negative energy density that defies normal physics. Unlike regular matter, which gravity pulls, exotic matter would repel space-time, creating the expansion needed behind the warp bubble. Think of it like trying to inflate a life raft while someone's sitting on it, except the raft is the fabric of reality itself, and the person is a spaceship trying to outrun physics. Here's where things get wild. Exotic matter isn't just rare, it may not exist at all. Quantum mechanics allows for fleeting particles with negative energy, like virtual particles popping in and out of existence, but scaling that up to warp drive quantities is like trying to power a city with static electricity from a balloon. Some theories suggest dark energy, the mysterious force accelerating the universe's expansion, might share properties with exotic matter, but we're light years from harnessing it. Even if we could, stabilizing a warp bubble is another nightmare. Tiny miscalculations could unleash runaway distortions, collapsing the bubble into a singularity or vaporizing the ship with lethal radiation. Yet the dream persists. NASA Eagleworks lab has experimented with tabletop warp field interferometers, hunting for microscopic space-time distortions. Meanwhile, physicists tweak Alcubierre's equations, searching for loopholes like oscillating warp bubbles that require less exotic matter, or warp highways where multiple ships share a single distortion field. The math hints at possibilities. A trip to Proxima Centauri, our nearest star, could theoretically take weeks instead of millennia. But here's the twist: even if warp drives are possible, they might be cosmic Pandora's boxes. Creating a warp bubble could generate catastrophic shockwaves in space-time, shredding anything in its path. Some models suggest the bubble's interior would accumulate deadly high-energy particles, cooking the crew. And then there's the ethical dilemma: arriving at a planet before the light from your departure does, effectively letting you outrun your own past. For now, the Alcubierre drive remains a tantalizing what if, a reminder that the universe's rulebook has margins, and humanity's just begun scribbling in them. So while we're not zipping to Alpha Centauri tomorrow, the mere fact that warp drives aren't impossible rewrites the future of exploration. The stars might not be as far as they seem if we can learn to fold the road instead of walking it. Somewhere in the depths of the cosmos, a silent killer might be lurking, not a black hole, not a rogue asteroid, but something far more insidious: phantom energy, a hypothetical variant of dark energy so extreme it could unravel reality itself. Picture dark energy as the universe's accelerator pedal, currently pushing galaxies apart at an ever-increasing speed. But what if that pedal gets stuck to the floor? Phantom energy takes dark energy's repulsive force and cranks it to nightmarish levels, growing stronger over time until space-time itself loses all cohesion. This isn't just expansion, it's a cosmic shredding machine, where the fabric of the universe stretches so violently that it tears apart everything bound by it, down to the very atoms in your body. The scenario plays out like a horror movie in slow motion. First, galaxy clusters held together by gravity would be ripped apart as the space between them expands faster than light can bridge the gap. Stars within galaxies would drift into the void, their gravitational bonds no match for the accelerating stretch of space. Then, as phantom energies grip titans, solar systems would disintegrate, planets torn from their orbits like marbles scattered across a rubber sheet stretched too thin. But the true horror comes last. Even the forces holding atoms together, the electromagnetic glue binding nuclei to electrons, would be overwhelmed. Molecules, then individual atoms, would be stretched beyond their breaking point, dissolving into a featureless haze of subatomic particles. No explosions, no fire, just a silent, inexorable dissolution of structure itself. The timeline for this big rip depends on phantom energy's strength, but some models suggest it could happen in as little as 22 billion years. That might sound comfortably distant, but consider this. If phantom energy exists, its effects could already be at work, hidden beneath the noise of cosmic expansion. The scariest part: unlike other doomsday scenarios, there's no escape. No bunker, no technology could withstand the unraveling of space-time itself. Even light would be stretched into uselessness, the universe fading into a cold, empty graveyard where not even the memory of structure remains. Yet phantom energy isn't just a doomsday tale, it's a stark reminder of how little we understand dark energy's true nature. Is it constant, as Einstein's cosmological constant suggested, or could it evolve into something far more destructive? The answer might lie in the fate of distant galaxies already slipping beyond our cosmic horizon, their light stretched into oblivion by forces we're only beginning to measure. Until then, phantom energy remains one of cosmology's most chilling what-ifs, a whisper in the dark hinting that the universe's greatest threat might not be collision or collapse, but the silent, unyielding stretch of nothingness itself. Zoom in far enough, past atoms, past quarks, down to scales so small they make a grain of sand look planetary, and the smooth fabric of space-time might dissolve into chaos. This is the quantum foam, a seething, turbulent layer of reality where the ordinary rules of physics break down, and space-time itself becomes a bubbling broth of virtual particles, microscopic wormholes, and fleeting distortions. Picture the surface of a stormy ocean, but instead of waves, it's space and time churning with spontaneous eruptions of energy. At this level, the universe isn't serene or orderly. It's a tempest where particles blink in and out of existence, borrowing energy from the void before vanishing back into nothingness. These quantum fluctuations aren't just theoretical. They've been detected indirectly through phenomena like the Casimir effect, where two metal plates placed incredibly close together in a vacuum experience a subtle push. Why? Because the quantum foam's froth of virtual particles can't fit between the plates as easily as they can outside, creating a pressure differential. It's like trying to clap underwater. Your hands meet resistance from the liquid, but in this case, the liquid is the roiling energy of empty space itself. But the wildest speculation centers on what else might lurk in this foam. Some theories suggest it's threaded with minuscule wormholes, Einstein-Rosen bridges so tiny they'd last only a Planck instant before pinching shut. Others propose that the foam's turbulence could create microscopic black holes, evaporating almost instantly due to Hawking radiation. These aren't just quirks, they're clues that space-time might not be fundamental at all, but emergent like the surface of water, which seems solid until you peer closely enough to see its molecular dance. The catch: we'll likely never observe quantum foam directly. Its scale is 100 billion times smaller than an atom's nucleus, far beyond any microscope's reach. Yet its effects ripple upward, influencing everything from particle behavior to the very fabric of gravity. If the foam is real, it means the universe's calm, predictable surface hides a frenzied underworld, a place where reality is constantly rewriting itself, and where the seeds of larger mysteries like dark energy or quantum entanglement might first take root. So while we skate atop the seemingly solid ice of space-time, beneath our feet lies a churning quantum sea, proof that even the void is alive with unseen fury, and that the universe's true nature might be stranger than we ever imagined. What if time travel wasn't just possible but mandatory? That's the brain-melting conclusion of Kurt Gödel's rotating universe, a cosmic model where the fabric of reality twists so severely that looping back into your own past becomes unavoidable. Picture a universe spinning like a colossal top, dragging space-time along with it like taffy on a spinning wheel. In this bizarre cosmos, the rotation warps world lines, the paths objects take through space-time until they curl back on themselves, forming closed time-like curves. Translation: follow the right path, and you'd end up right back where you started when you started, meeting your past self face to face. Gödel, the same mathematical genius who shattered logic with his incompleteness theorems, crafted this model in 1949 as a birthday gift for Einstein. It was more than a thought experiment, it was a deliberate challenge to relativity's foundations. Einstein's equations allowed for time loops, but Gödel proved they weren't just quirks. They were inevitable in a universe with enough spin. His solution revealed something shocking. Under the right conditions, the universe's rotation would force causality to break down entirely. There'd be no before or after, just an endless Mobius strip of events feeding back into themselves. Here's where it gets even weirder. In Gödel's universe, you wouldn't need a wormhole or a warp drive to time travel, just a really fast spaceship. Fly a sufficient distance along the universe's axis of rotation, and you'd circle back to your starting point in time as well as space, like a record needle skipping back to an earlier groove. This isn't the grandfather paradox waiting to happen, it's worse. In a Gödel cosmos, paradoxes aren't just risks, they're baked into the geometry of existence. The universe wouldn't just allow time loops, it'd demand them, weaving them into the daily rhythm of reality. Of course, observations suggest our universe isn't rotating globally, at least not noticeably. But Gödel's model remains a profound cautionary tale. If relativity permits universes where time is a pretzel rather than an arrow, what does that say about the nature of causality? Are we living in a cosmic exception where time flows neatly forward, or is our linear perception just a local quirk of a far stranger multiverse? The answers might lie in the voids between galaxies, where faint traces of universal rotation could still linger, hidden in the whisper of primordial gravity. Until then, Gödel's spinning cosmos stands as a reminder. The universe doesn't owe us intuitive physics, it only owes us consistency, even when that consistency looks like madness. Black holes aren't just cosmic vacuum cleaners, they're demolition experts with a knack for shredding the universe's receipts. Here's the problem: quantum mechanics insists that information, the fundamental blueprint of reality, can never be destroyed. Even if you burn a book, the ash and smoke still encode the book's information in some messy, scrambled way. But black holes seem to break this sacred rule. When matter falls past the event horizon, it's gone, crushed into oblivion at the singularity. No ash, no smoke, no hidden quantum traces, just a one-way trip to nowhere, leaving a glaring paradox at the heart of physics. If information truly vanishes, then quantum theory is wrong. And if it isn't lost, where does it go? Stephen Hawking threw gasoline on this fire in the 1970s when he showed that black holes don't just swallow matter, they evaporate. Through quantum trickery at the event horizon, they emit tiny particles now called Hawking radiation. Over eons, this slow leak causes black holes to shrink and eventually vanish. But here's the catch: Hawking radiation appears random, carrying no trace of the information that fell in. It's like shredding a priceless manuscript and claiming the confetti holds no clues to the original text. This revelation sparked a decades-long crisis. If the radiation is featureless and the black hole disappears, then the information it swallowed is erased from the universe forever, violating quantum mechanics' core tenets. The stakes couldn't be higher. Quantum theory underpins everything from chemistry to computing, and if black holes break it, we're missing something profound about reality. Some physicists, like Leonard Susskind, refuse to accept information loss. They argue the information isn't destroyed, it's transformed, imprinted onto the event horizon like a hologram. Imagine throwing a chair into a black hole. From the outside, the chair's information gets smeared across the horizon in quantum pixels so fine they encode every atom's position. The chair's essence isn't lost, it's painted onto the black hole's surface in a quantum cipher, eventually leaking back out via Hawking radiation. This holographic principle suggests black holes are cosmic archivists, not shredders compressing 3D information into 2D code. But others, like Roger Penrose, counter that quantum mechanics itself might need rewriting. If information can vanish, then our understanding of reality is incomplete, missing a chapter where the rules bend under extreme gravity. The debate even split Hawking himself. After years insisting information was lost, he famously conceded in 2004, placing a bet and losing that black holes do preserve information somehow. The twist: we still don't know how. Recent breakthroughs hint at answers. The discovery of soft hair, low-energy quantum fluff around black holes might store bits of information like cosmic barcodes. And firewalls, hypothetical walls of energy at the event horizon, could scramble and return information via Hawking radiation. But these ideas remain hotly contested. The paradox forces us to choose. Either quantum mechanics is flawed, or black holes are the universe's most sophisticated cryptographers, hiding secrets in ways we've yet to crack. One thing's certain, this isn't just academic squabbling. The information paradox is a battle for the soul of physics, a clash between quantum theory and gravity where only one can emerge unscathed. And until we solve it, black holes will keep taunting us with their cosmic magic trick, making reality disappear without a trace. Even in the deepest void of space, where darkness stretches for billions of light years, there's no such thing as true emptiness. What looks like nothingness to our eyes is actually a seething quantum storm where particles and energy burst into existence and vanish faster than a blink. This bizarre phenomenon, known as quantum fluctuations, means that space-time is more like a turbulent ocean than a still pond, even in the most deserted cosmic deserts. Picture this: at scales so small they make atoms look like planets, pairs of virtual particles, one matter, one antimatter, constantly blink into being, borrowing energy from the universe itself before annihilating each other in a flash of oblivion. These aren't just theoretical ghosts, they leave tangible fingerprints on reality. The Casimir effect proves it. Place two metal plates incredibly close together in a vacuum, and they'll be subtly pushed toward each other. Why? Because the space between the plates is too narrow for certain quantum fluctuations to occur, while the space outside remains a riot of particle pairs. The result, an imbalance in pressure, proof that so-called empty space is anything but empty. But here's where it gets wilder. These fleeting particles aren't just cosmic background noise, they can shape the fate of the universe. Black holes exploit this chaos through Hawking radiation. At the event horizon, a virtual particle pair might split, with one falling into the black hole and the other escaping. The escaped particle becomes real, stealing a tiny bit of the black hole's mass in the process. Over eons, this quantum heist causes even the mightiest black holes to evaporate. Quantum fluctuations might also hold the key to one of cosmology's biggest mysteries: why the universe exists at all. During the Big Bang, a random fluctuation in the primordial quantum foam could have tipped the scales, creating slightly more matter than antimatter. That tiny imbalance, just one extra particle in every 10 billion, allowed our universe to avoid immediate annihilation and blossom into the cosmos we know. So the next time you gaze at the night sky and feel the weight of its vast emptiness, remember, there's no such thing as nothing. Every inch of the universe, from the void between galaxies to the air in your lungs, is a carnival of quantum creation and destruction. A reminder that reality's foundations are far stranger and far more restless than they appear. What if the very act of looking at the universe changes it? This isn't just philosophy, it's one of quantum mechanics' most baffling puzzles. The observer effect suggests that particles don't settle into definite states until they're measured, as if reality itself hesitates until someone's watching. Take the famous double-slit experiment. When unobserved, electrons behave like waves, creating interference patterns on a screen. But the moment you install a detector to see which slit they pass through, they switch to acting like particles. It's as if the universe knows when you're peaking, adjusting its behavior like a self-conscious performer. Now crank this idea up to cosmic proportions. Some theorists propose that consciousness isn't just a passive witness but an active participant in shaping space-time. In this radical view, the fabric of reality might remain blurry, like a half-rendered video game, until a conscious observer collapses it into solidity. Think of Schrödinger's cat, alive and dead simultaneously until someone opens the box. Could the entire universe exist in a similar quantum haze until life emerges to perceive it? This idea, dubbed the participatory anthropic principle, suggests space-time itself might crystallize around conscious observation, weaving existence into being through the act of witnessing. The implications are dizzying. If consciousness knits reality together, does that mean empty regions of space remain unrealized quantum potentials until observed? Could distant galaxies flicker in and out of existence based on whether anyone's looking? even Einstein grappled with this, famously questioning whether the moon disappears when no one's watching. While mainstream physics balks at such extremes, the line between observer and observed blurs at quantum scales, leaving room for speculation. Some interpretations of quantum mechanics, like the von Neumann-Wigner hypothesis, go so far as to place consciousness as the ultimate arbiter of reality's structure. But here's the twist: if consciousness molds space-time, what about artificial intelligence? Does a self-aware robot count as an observer, or is there something uniquely biological about perception? And what happens in a universe teeming with alien civilizations? Does their collective gaze solidify cosmic structure faster? These questions straddle the border between physics and metaphysics, challenging our most basic assumptions about existence. While hard evidence remains elusive, experiments in quantum biology hint at deeper connections. Photosynthesis, bird migration, and even human smell rely on quantum processes, as if life evolved to exploit the fuzzy edges of reality. Whether consciousness truly bends space-time or merely reflects its quirks, one thing's clear: the universe isn't just out there. It's in here too, tangled up with the very act of perception in ways we're only beginning to fathom. And that makes every glance at the night sky not just observation but collaboration. From bending black holes that slow time to a crawl, to quantum foam bubbling beneath reality's surface, we've journeyed through a universe far stranger than fiction. Space-time isn't just a backdrop, it's a dynamic, twisting stage where the rules rewrite themselves under extreme conditions. Think about it: wormholes could bridge distant galaxies, entire universes might be holograms projected from a 2D edge, and particles communicate instantly across light years through spooky entanglement. Even the vacuum of space isn't empty, it's a quantum storm where particles pop in and out of existence, shaping the cosmos itself. Yet for every mystery solved, a dozen more emerge. Why does dark energy push the universe apart faster and faster? Could phantom energy one day tear reality apart? Are we alone, or is the silence of the cosmos a chilling sign that advanced civilizations manipulate space-time in ways we can't yet fathom? The wildest part: these aren't plot twists from a sci-fi epic, they're real questions physicists grapple with daily. So what's your take? Did the twin paradox bend your mind, or does the holographic principle make you question everything? Drop your favorite fact or wildest theory in the comments below, and if you're hungry for more cosmic mysteries, hit subscribe. The universe is full of secrets waiting to be uncovered, and we're just getting started. After all, as Einstein once said, the most beautiful thing we can experience is the mysterious. And in this cosmos, mystery is the one thing we'll never run out of.